I think we have 3 classes left, right? So my plan today is to tell you about the Schrodinger equation. And then maybe next time I'll tell you a little bit about measurement theory, which is kind of like interesting just because that involves like self-adjoint operators. And maybe like the last time just mentioned like some of like the qubits, quantum computation, all this stuff, which is more like applied. And it has like the advantage that like, it's just like linear algebra of finite matrices, so it's kind of fun to see like the application, like the ideas there because it's like all very concrete. So like it's kind of like just like come back to earth and like, have like something more concrete to think about. So what, yeah.
Okay, can there be any assignments or final projects for this?
I think we can not like, not really. Like if you want to, like I can suggest some, like if you wanted to do some research, like learn something about specific, I can just give you some suggestions. But yeah, I wouldn't worry about that, yeah. So but yeah, so I don't couldn't come up with anything to agree to. But yeah, if someone wants, like, if after this, like anyone is interested in something specific, then yeah, I'm happy to just provide some references or like check out what you were looking into. So let me just write the Schrodinger equation, like the full generality. So that's what I was trying to explain last time. So the idea is this is for a particle of mass m. So just think about it like, I mean, in the same way as like in classical mechanics, maybe you have like a point particle. The idea now is that you associate to the particle a function, which is called a wave function. So you associate to this wave function. Okay, so if you think about the particle, like just like in one dimension, so let me start here with one dimension. Then the wave function is supposed to depend on the position of the particle and time. Now the idea is that this will be complex value in general, so that's kind of like the first important thing. So it is complex value. So it just takes like complex. It could be, could be things like this. It could be like a complex exponential, for example. Not that this is going to solve the Schrodinger equation or anything like that. I'm just saying, like the values are like complex. So, and like the usual decomposition of a complex number is like, if you remember, like complex numbers typically are written in 2 ways, right? In terms of the real imaginary part or in terms of the polar decomposition. So here I'm more, if I write something like this, I'm thinking more like in the polar decomposition where it's just like a real number, right? Which is kind of like R, which is not negative, right? Like the amplitude or the norm squared. Well, the length of the complex number times purely imaginary number, like, well, like not purely imaginary, but rather like something on the unit circle, like the phases. So anyways, like the point is that this is like complex value in general, so that's different from like the other types of equations we had studied before. And the point is that it satisfies, so you call a function of these two variables a solution to the Schrodinger equation if it solves uh, so that is the Schrodinger equation. Where here you're thinking of V as before, like the potential energy. So here, like, well, just to, yeah, like clarify some notation. So I is just like, yeah, square root of -1. H bar is, it's just like a constant that appears in physics, so it's like a constant related to Planck's constant. It's basically Planck's constant over 2 pi, but it doesn't matter too much. So just think about it as a constant. M is the mass, as I mentioned before. What else do I need to explain here? And D is like the potential. Okay. So that is how the Schrodinger equation looks like. So my point has been to kind of try to relate this to classical, I mean, what I was going to do today is kind of just to show you how it's related to the other stuff we have discussed about Hamiltonian mechanics and on, so that it doesn't look that different from what we have discussed before. So let me just like make a few remarks. So one of the interesting things about the equation is that it involves only one partial derivative with respect, like one derivative with respect to time, right? So it's only involves a derivative with respect to time, which in this case, which is different from like all the other equations we have studied before. So let me put this as remarks. Let's call this as E for Schrodinger equation. So it involves first derivative in respect to time. Contrary to something like Newton's equation, which is second order in time, right? Like because it's with acceleration, or the wave equation, which if you remember the wave equation is also second order in time. So which is different from. Okay. Now at the same time, so like that looks different, but is not that different in another sense because you know, you can, if you remember, like you can rewrite like Newton's equations as a system of first order ODEs. Like for example, if you introduce like another variable, which was the momentum. Here, there's something slightly similar that you could do, which is, because this is complex value, right? Since it's complex value, you could always decompose like a complex function into real and imaginary parts, right? So just to emphasize this, but if you write, if you decompose, imagine you had like a solution, or you think about this equation as an equation for the real part of the function plus the imaginary part of the function, or You could also decompose it like using the polar decomposition. You could also think about it as a, let's call this theta xt. You know, if you break the explicitly like complex function into real imaginary or the polar decomposition, then like you can, you would substitute this into the Schrodinger equation and split the Schrodinger equation into the real and imaginary parts. So what I'm saying is that you can think of this as a equation for, as a system of two equations, one for like, one equation for the real part, another equation for the imaginary part, or one equation for the polar part and another equation for the angle, right? So you can think of this as, so in terms of like the real functions, in terms of this decomposition, it does become a system of first order ODEs. A system, it becomes a system of two different differential equations. Which are first order in time, which is not that different in a sense from how Newton's equations look when you, for example, rewrite them in Hamiltonian form, which are first order in time. So in a sense, since like a complex function is two real functions, right? This is really like a system of two equations. It's just that typically you do want to, it is kind of more convenient to think of psi as a single entity, right? And not necessarily break it into the pieces, but it actually, in a few minutes, I'll kind of tell you what this, if you break it into the polar decomposition, what the equations look like, and that can be useful. All that I'm saying is that, in a sense, like this is kind of two equations in one. So it's not that different from like Newton's equations, which were also like two equations, one for the position and one for the momentum. It's just that in this case, like you don't think that, in a sense, like the position of the momentum is the derivative of the position is the momentum. So like in Newton's case, like the two functions are related, or here you're not necessarily thinking that the real part and the imaginary part determine each other, right? It's not that the one is a derivative of the other or something like that necessarily. So okay, but still, it's first order in time. So if you were to try to solve it, you need to specify like an initial condition, and that would be kind of like the wave function at time zero. Okay. So that's the first thing to say. And the other thing to say, if you notice it, is that this equation is linear in psi. Right, size appears psi to the power 1. So, and that's kind of one of the important things of this equation. So it is a linear equation. So, meaning that if you have two solutions and then if psi 1 of xt, psi 2 xt solve the Schrodinger equation, then any linear combination where here because it's a complex equation, you can take the coefficients to be complex numbers, right? Wait, they don't have to be real numbers. And it solves it. Which is kind of what does make quantum mechanics interesting from a mathematical perspective, because all the quantum mechanical systems are linear, like at least when you're modeling them with the Schrodinger equation, which is not true in classical mechanics. So in classical mechanics, yes, if the Hamiltonian is kind of quadratic, which is the case that we study most of the time, then yeah, the equations become linear. But for more general Hamiltonians, like the equations are not linear. So you cannot just like add two solutions what I'm trying to say is that in classical mechanics, you cannot just add two solutions to Newton's equations and get another solution. When that happens only in very special cases like Hooke's law, other things like that. In most situations in classical mechanics, like there's like, uh, the space of solutions, is not a vector space, but that does happen basically every single time in quantum mechanics because the Schrodinger equation is always linear. So that that is one of the main features of this equation. So okay, now the first thing that I want to do is kind of relate this to Hamiltonian mechanics. So there is a relationship with Hamiltonian mechanics, and that also gets us into the topic of quantization. So let's talk about this here. I do want to leave the equation on the board, so that I can keep referring to it. So let's just relation to Hamiltonian mechanics. So just to remind you of how I'll do it for the wave equation because it's more similar to the Schrodinger equation in a sense. So if you remember, like the wave equation was something like this. Where this represented the velocity of the wave. And I had mentioned before, like, you can rewrite this as a system which is first ordered in time, Okay, so if you remember, like here, like just by analogy with the case of a particle, you could define kind of like a momentum for the wave, which was the momentum was just like the derivative of the function u with respect to time. So if you do it that way, right, to kind of reduce, like to make it consider this as a system of two first order partial differential equations, then the derivative with respect to time is the momentum. And then the derivative of the momentum would be the second derivative of u with respect to time. So that should be the velocity of the wave squared times this thing, which I'm rewriting as a second derivative with respect to x of u. Okay. And so that, if you just play that a little bit with the equation, we could rewrite it in this way. If you know, so like, just you can check you're doing the matrix multiplication. So this is the matrix that we usually call J before. And this was like the Hamiltonian matrix in this case. So I'll call it like Hamiltonian matrix. Okay. So if from this perspective, then the wave equation was the derivative with respect to time of u pi is J times the Hamiltonian times u pi sub p. Okay. So and in fact, if like just to make this like look even nicer, like you could call all of these vector, you could call what? Let's try to not use like a bias name. So I'll call it you call that vector phi, then like you're saying that the derivative with respect to time of phi is J times the Hamiltonian matrix times phi. right? Okay, so by, like, what I'm going to do is kind of rewrite the Schrodinger equation in a way that formally looks the same as this, okay? So how will I do that? Let me do this for you. Okay, so let's just think about this matrix J. What was the important thing of this matrix J? Uh, the important thing of the matrix J was that it squares to minus the identity, if you remember that. So, you know, so in linear algebra, this is what is usually called like almost complex structure. So an almost complex structure in a vector space is a matrix or a linear transformation whose square is minus the identity. Um, So in a sense, that is like an analog of multiplication by I, right? Because I is something whose square is minus one. Okay, so what I'm saying is that you should think of J as a version of I or negative I. That's kind of like the role that's playing here. So there's already like an I in this equation. So I'll just move it to the other side to kind of make that look better. So if you multiply both sides of the equation by I, okay, so well, because, when you multiply it, you get like on both sides, or you just divide by I on both sides, however you want to think about it. Oh, in fact, like, let me put it like this. You can rewrite the equation, which makes it more clear that this is like linear inside. Okay, so you can rewrite the Schrodinger equation this way. Okay, so if you compare it, I can ignoring the H bar here, like this saying, like the derivative with respect to psi of t, then it should be J, right? So you should identify, like, the idea is to kind of think of this as being like J, because it's something whose square is minus one, right? So this is kind of like the J here. And then psi should match this. So whatever you have in the middle should be what you call the Hamiltonian. Okay, so the idea is to think of the Hamiltonian in this case. Okay. And I'll put like a hat, usually like that's like quantum mechanics, that's like the name that you give to this. But in this case, then the Hamiltonian associated to the system. So in this case, one takes H, the Hamiltonian to be okay. But let's just make this more clear. Like the typical Hamiltonian, right? Like if you wanted to make this analogy kind of work well, like the typical Hamiltonian, right? And for a particle, what was a Hamiltonian? Like for a regular classical particle, like for a classical particle, what is a Hamiltonian? The Hamiltonian was like p squared over 2m plus the potential energy, right? That was like the traditional Hamiltonian that we saw, right? So by comparison, if you wanted to identify, like, kind of think of this like as a quantum version of this one, you should think of whatever this is as like the quantum version of this, right? So you kind of, well, they both have like the factor of 2m, right? So what I'm trying to say is that the momentum, right? So the momentum squared. So, we should identify uh, p squared. I mean, the 2m is the same, so you should like think of the momentum as being minus h bar squared times dx squared. Okay. But what is this? Again, this is like you should think about this as an identity between what people call operators or like matrices of infinite size, if you like. So what I'm saying is that like to make the analogy perfect, what you should kind of change is like the momentum into this kind of quantum momentum or like the momentum, what's called like the momentum operator. And so the momentum operator should have the property that its square gives you this thing. Okay, but now how can you think about this? Like, well, if you send the other this to the other side, you get this. And if you use complex numbers, you can apply the difference of square formula, right? So you can write this as p hat plus I h bar dx times p hat minus h bar dx equals 0. That makes sense? That works, right? Like the difference of square works fine if you include the number I. And so if you wanted this equation to be satisfied, you have kind of two options here. You could just make p hat, like, just to make this automatically be true, you could just like force it to be one of these two factors. Okay, so that like, or force one of these two factors to be 0. That's what I'm trying to say. And if you force one of these two factors to be 0, then obviously the previous one would be true as well. So usually, the way you think about this problem, like we make the first choice, and you'll see why in a moment. So the way to think about this is that the momentum of the particle. So the momentum of the particle becomes this thing. Okay, and it kind of is important to think about what you're doing here. So when you have like a particle in classical mechanics, right? If you have a particle in classical mechanics of mass m, the momentum is just mass times velocity, the most like easy case, right? So it is like a number or a vector at most, if you think about this like in 3 dimensions. But if it's on the line, this is just like the classical momentum is just a number, right? But what I'm saying is that like the quantum momentum, what you would like to call the quantum momentum, so that it matches like the Hamiltonian formulation, cannot be a number because it's like a derivative with respect to x, right? So it becomes an operator. So here, this you can call it the quantum momentum operator. Right here, like the momentum of the particle is not a number, it is an infinite matrix, or like this operator. So it is now an operator or infinite matrix, if you like. No. Okay. So from this perspective, you can think of from this perspective, and this is what's related to what people call quantization. So quantization is where you have like a classical system. You know, it's where you have like a Hamiltonian, right? Like a Hamiltonian describing a classical system. What are some Hamiltonians describing classical systems? So for example, it could be the Hamiltonian of the free particle, which is p squared over 2m, or it could be the Hamiltonian for the Hooke's law. I don't know if you remember Hooke's law, which would be p squared over 2m, what like 1/2 k x squared. Like that was a Hamiltonian for Hooke's law. And the point of if you wanted to like so this is kind of like what the Hamiltonians that describe like a classical particle. And then in quantum mechanics, there is like a corresponding Hamiltonian that describes like the quantum version of the particle. So this can be turned into a Hamiltonian for like the quantum mechanics system, which is like, and this process is called quantization. And the way you obtain it is just by replacing P. You replace P with this representation. So P squared would become, P squared will become minus H bar squared dx squared. And like, for example, here, the, the Hamiltonian for this system is P squared, oh, sorry, over 2m. It's just what you get by replacing the Hamilton, like the momentum with this operator, and like x, you can just leave it as it is. So the quantization is kind of like a process where you take the equation of classical mechanics and turn it into like an equation for quantum mechanics by just like finding the corresponding Hamiltonian and associated to this using this like rule. Does that make sense? It can be confusing at the beginning when you think about this. Because again, the idea, maybe to emphasize this, like the idea is in classical mechanics, for example, for a particle, Newton's equations are an equation for the position and the momentum of the particle. So there are equations for numbers, like the position and the momentum are numbers, right? In quantum mechanics, the equation is not for the position or the momentum of the particle in the traditional sense of the word. The equation is for the wave function. So there is no equation for position, like in the traditional versions of quantum mechanics, there is no equation for the position of the particle in quantum mechanics. There's only the wave function. This is the only thing that exists. And the idea is like, if you want to find the corresponding equation that the wave function is supposed to satisfy, you can do this trick where you can take the Hamiltonian from classical mechanics and quantize it, which is how people call that. But it does have like a different flavor because there is no like that directly like an equation for the position, for example, or something of that sort. Now, so what is like a nice thing about this? Okay, so I don't know if you have done this before with complex matrices. So let me just do it in a 2x2 case, like just a small detour or remark. if you have a matrix, it's just like all real numbers, right? Then we had the transpose, right? Like, so the transpose, oh, you know what it is. Change rows with columns, whatever. If you have a matrix that has complex numbers as its entries, right? Let's do another matrix. You could still transpose it, right? But the transpose is not a very useful notion once there are complex numbers involved, right? You have to take the adjoint. I don't know if you have seen that before. So have you seen the adjoint of a matrix before? Like usually you put like a dagger or an asterisk, depending on the notation you use. I'll put like an asterisk just to, because it's probably more closely related to like the math literature. The physicists would tend to use more like a dagger for this. So what is the adjoint? The adjoint is the transpose conjugate. So you transpose it but conjugate each entry. So that is like the better. So let me put it like this. Like, so you would say, so for example, like this gets conjugated, and the conjugate of I plus one plus I is I, one minus I. This one gets conjugated and goes to the bottom, so it becomes I. This is completely real, so it's its own conjugate, right? And this one becomes 3 minus 2I. And just to remind everyone, like the conjugate of x plus IY is x minus IY. Right. Um, then the reason why this is kind of nice is like because the correct analog of being symmetric is not that you equal your transpose, but you equal your adjoint. So being like for complex matrices, what you like, for complex matrices, what's important, like the useful condition is like to be self-adjoint. So complex matrix is self-adjoint. If it equals its adjoint. So it's no longer symmetric because being symmetric is not that useful in the complex case. So for example, these are the ones whose eigenvalues are all real and for which there's a spectral theorem. And, like usually the properties of symmetric matrices continue to work for self-adjoint matrices. Okay, so why do I bring this up? Because the reason what happens here for something like this, again, think about this some sort as it's an operator, but you can think about it as some sort of matrix. So you could ask, what's the adjoint of this thing? Okay, what is the adjoint of this operator? Okay, so it is like conjugating and transposing at the same time. So when you conjugate, this minus I becomes plus I, right? H bar is like a constant, it's just like a real number, like it's like a real number. So like conjugating does nothing to it. And then this is kind of like the matrix part of this expression. So this, I mean, in a sense, real. So you just transpose it. And we had seen before, let me just change this into I. So we had seen this before, but the transpose of the derivative operator was minus the derivative operator. This becomes I H bar times minus the derivative operator. And so you get minus H bar derivative operator, but that is P hat again, right? So the point here is that this momentum operator is self-adjoint. Okay, so Or if you don't want to think about it in complex numbers, just think about it as being almost like symmetric. It's self-adjoint. Okay, so being self-adjoint in this case means that all these eigenvalues would be real. And usually in quantum mechanics, the eigenvalues is what you identify with the things that you can measure of the system. So the eigenvalues are real. And these eigenvalues correspond to the things that you could, like the momentum that you could measure of the electron or the particle, which would correspond to the values of the momentum you could measure. You can measure. So what I'm trying to say is that, if you have an electron, like just to try to explain it again. So if you have an electron, its momentum is not a number, it's a matrix, it's an operator. So that's weird because as you say, how can you measure like, what does it mean to measure like a matrix, right? Like, so in this context, in the context of quantum mechanics, measuring the matrix means measuring one of the eigenvalues of the matrix. Okay, so the things that show up in experimental results are only the eigenvalues of matrices, like, or the operators, actually, to be more precise. So that kind of like clarifies what appears a bit like puzzling at the beginning, because it is weird to think of the momentum just as a matrix, right? When before in classical mechanics, it's literally a number. So the conundrum is solved by saying, oh, it's actually the eigenvalues of that matrix what you measure, which is a different story, like why does that happen? Like that's like one of the funny things about quantum mechanics. But if you take that for a fact, then that is how you always would keep getting numbers at the end of the measurements, because the numbers just correspond to the eigenvalues. So in that sense, similarly, just to, so I was saying that like the Hamiltonian operator for a particle would be, again, like, so this is like what I would call the Hamiltonian operator. So again, like for something like an electron or something like another subatomic particle, the Hamiltonian is not a number, right? Before, like in classical mechanics, the Hamiltonian wasn't like a function or a number, depending on how you want to think about it. The Hamiltonian is not a number, it is an operator. So it's an operator, but this one is still, it's also self-adjoint. So just like similar to the momentum, what you would measure, you don't measure the operator directly. You can only measure the eigenvalues of the operator. The eigenvalues of the operator would be real, and that's what you would identify with the energy of the particle. Because if you remember, like the Hamiltonian was kind of like the energy of the particle. So the eigenvalues of this thing would correspond to the possible energies of the particle corresponds. Is that making sense? So again, like you don't measure directly, like there's kind of like now a two-step process where like the quantity itself becomes like a matrix, and then you measure the eigenvalues of that matrix. So you don't deal directly with the quantity. And what kind of happens if you like, well, we don't have time to get into that example, but if you you can solve like the hydrogen atom, that's like kind of like the first example that you do in quantum mechanics. So just kind of like an electron orbiting along a proton. And what you would find there is that the eigenvalues here are discrete, meaning that they're not continuous. So like the electron can only take certain energies on the when it's orbiting the proton, and that kind of like if you ever had to take it in high school chemistry, whatever, like the Bohr model, the hydrogen atom, and all this stuff, where like it can only kind of like, it's not like the positions like the electron can take are not kind of just continuously, it's just like certain values. So, the point here is that, there is a two-step process, because first you kind of turn the quantity that you remember from classical mechanics into an operator, and then the eigenvalues are what the things that you can measure. So maybe I should put it, more like in words again. So you have like in classical mechanics, things that you care about, like momentum, energy, well, position as well, but angular momentum, other things, etc. And then you do something that's called quantization. And so you get to quantum mechanics, and then you get the momentum operator. So operator, then you get the energy operator, etc. So these are all numbers, and these are all operators or matrices. And then the eigenvalues of these things are the things that you would deal with on an experiment, for example. And then you measure. Is that okay? Is that making sense? Okay. And maybe next time I'll do the finite dimensional case to work out something that's a bit more concrete. And that's kind of fun because it's like the stuff that's related to quantum computation. Because otherwise it would get too abstract. But so my point is that because of all of this, like the Schrodinger equation, if you like, then the Schrodinger equation is h bar, the derivative of psi with respect to t, equals minus h, sorry, negative I, the Hamiltonian operator times psi. Or the way that's usually written, or IH bar, the derivative of psi with respect to t, equals h hat psi. Okay, so that is traditionally the way you would see the Schrodinger equation written as. Like it's a derivative, an equation for the derivative of the wave function with respect to time, and it's saying that its time derivative must equal, the value, the Hamiltonian operator on acting on that function. Okay. So in that sense, it takes essentially the same shape as like the equations of classical mechanics, when those equations are linear, because that's basically how you can rewrite the wave equation or like Newton's equations in the linear case. So in that sense, like quantum mechanics is like a version of Hamiltonian mechanics, but for functions and operators instead of like position and momentum and other things of that sort. Okay. Um, but yeah, so the other like I think today the other thing I will mention is like other relation it has with Hamiltonian mechanics. And then next time I think it may be better if I just choose something very concrete. So I'll do kind of like spin, which is like a very nice application of quantum mechanics. And there you can understand everything because it's with complex 2x2 matrices. So there, like, there is no problem, kind of like making this very concrete. And it's kind of nice to see like in an actual thing that's quite relevant today. Because have you seen the tensor product of vector spaces? Okay, cool. So that is like a very fun, like that is, okay. I don't want to enter into what makes quantum mechanics paradoxical per se, but, you know, we should talk about the tensor product next time because that's one of the things that makes quantum mechanics particularly fun to work with. So let me just like say something first, and if I have some time, I'll tell you about like tensor products. Um, So the other relation with, there's a second relation with Hamiltonian mechanics, which is the following. If you remember, like, you have the Schrodinger equation. Let me rewrite it. I shouldn't have deleted it. Okay, so this is an equation for like a complex value function, as I said, but you can write like the wave function as like use the polar decomposition. So, like the polar decomposition for a number is like the modulus, like, the norm of that complex number times the phase. And I'll write the phase as e to the I times of xt over h bar. Okay, so you'll see why in a moment. Where here, like this is kind of like what before I was writing as e to the I theta. Okay, and so like it does take a bit of time, but if if you plug that in back, if you can kind of use this composition, plug it into the Schrodinger equation, and so you get like an equation for like, you can break it into real and imaginary parts. So you substitute this into Schrodinger, substitute in Schrodinger equation, and get two equations, one for the real part and the other for the imaginary part. Get two equations. So it's like a bit tedious, so I won't do it here, but you get these two equations. So uh, Okay, so that's what you get if you work everything out. Uh, okay, and so. Okay, so without getting into too many details, the point is that, like, we didn't spend too much time talking about the first equation. So I won't mention this, but there's like an interesting interpretation for the first equation. But the second equation, this is the same thing that appeared when you had this Hamilton-Jacobi equation. So if this were zero, if this were zero, that means that S would solve the Hamilton-Jacobi equation. The Hamilton-Jacobi equation was like this canonical transformation that you would do to make the Hamiltonian become zero. So it's like and this would say that S solves the Hamilton-Jacobi equation. So you may want to go back to check that again. But my point is that, the other reason why this is related to the Hamiltonian mechanics is because, I didn't say this, but H bar is called Planck's constant, so, you have to think about it as kind of being small in the macroscopic world. It's only kind of important for quantum mechanical systems. So if you think in the way to think about like classical mechanics is some sort of sense of limit where like H bar is really close to zero. So if you think of this as being close to zero, it's essentially like the equation from classical mechanics. So that is kind of useful if you want to see how you can recover classical mechanics from quantum mechanics, like rewriting the equations in this way. And the first equation, again, I won't get into these details, but this is some sort of like continuity equation. But yeah, I think for the last two classes, I'll take more like an approach of like finite dimensional linear algebra, just to make things a bit more concrete. So just to get that started for next time, it is useful to talk about like the direct sum of vector spaces versus the tensor product. So have you seen direct sum before? Let's see. Let me do like an example. So yeah, like this is kind of like a basic introduction to some of the quantum mechanics stuff, but next time I'll just work out like a more specific example with finite dimensional matrices. So let's just, when you have vector spaces, there are two operations that you can do with vector spaces. One is called the direct sum and the other is the tensor product. So direct sum. So I'll illustrate it in the case of Rn because that's the easiest way to understand it. And so for example, let's say I'll take the vector spaces to be R2 and R3. Okay, so just even to make it even more like concrete, right? Like let's say what is a vector in R2? Vector in R2 would be like 1, 2. What is a vector in R3? Let's put like, the minus 1, 1, let's say 2, 3, right? Something silly. So what would it be to take the direct sum of these vectors if in this very concrete representation, taking the direct sum of these vectors, which is usually how you would write it here, it's just like stacking one vector below the other. Like, if you think about it as column vector. So like, just because I wrote this first, it's 1, 2, and then I put the entries of the other one right below that one. So negative 1, 2, 3. Okay, so now that gives you a vector in R5, right? So because now the vector has 5 entries, right? So more like basis independent way, like, like the idea is like, if you had like a vector sum, if you had like a vector space with basis V1 up to Vn, and another vector space with basis W1 up to Wm, like then a basis for the direct sum is just like the basis for the first one followed by the second one. But in this case, the way you should think about this is that the loops in R5, and so like the direct sum of R2 with R3 is just R5, right? And in general, like like the direct sum of Rn with Rm is Rm plus m. Does that make sense? That makes sense good. Kind of reasonable. So in general, like, if you have two vector spaces which are not V and W, the dimension of the direct sum, the dimension of V plus the dimension of W. I'm just cheating a little bit because, any vector space is isomorphic to like an Rn, right? For some n. So I'm just cheating just to show you how it looks on Rn, but it's essentially the same construction. It's like like I'm showing it in a way that's kind of basis dependent, but there's a more fancy way to do this. But like the point is that when you take a direct sum, the dimensions add up, right? But then the tensor product is like genuinely a more interesting construction. So this is like the direct sum. And so what that as a as a extreme case of this, what if you had n copies of the same vector space, right? So, and let's say these are n copies of the same vector space, then it's just the dimension for this will be n times the dimension of B, right? Like that, so like the dimension is just additive for the sum construction, which makes sense. Like it's called like the direct sum, so it would make sense that for the dimensions to add. Okay, but what is a tensor product construction? So let me again illustrate it for like R2 and R3. So let's take R2 and R3. Okay, so what would it mean if I wanted to do the tensor product of these two vectors? Which is usually this way how it's represented. Okay, well, you see like something that looks like a multiplication, so probably there will be like a multiplication of sorts involved, right? So the idea of like the tensor product is that you like again in this basis representation is that you multiply each entry of one vector but for times the corresponding entries of the other vector. So for example, I'll do like I'll do the first entry of B with the first entry of W, that gives you 1, -1, that gives you -1, right? Then first entry of B with the second entry of W gives me 2. And then first entry of B with the third entry of W gives me 3, right? And then you do the same for the second entry. So 2 times -1 is -2. 2 times 2 equals 4, and 2 times 3 equals 6. Okay. So like the entries here, the entries here, are just a kind of product of the individual entries of the two vectors. Is that okay? Is that making sense? And so how many entries does this vector have? It has 6 entries, right? So now this is like a vector of R6, right? And then what is that? So what does that mean? It means that that would mean that R2 tensor product R3 is R6, right? And more generally, what would happen that Rn tensor product Rm is just R to the n times n. Okay? Is that okay? And so, for the because of the tensor product construction, the dimension of a tensor product is the dimension of B times the dimension of W, right? Which is what I'm writing here. And so if you take the tensor product of a vector space with itself n times, right? Like so let's say this is n times. What does that mean is what would the answer be? Dimension of B to the n, right? That makes sense. Okay. So what that means is that the direct sum, the dimension grows linearly, right? Whereas the dimension for the tensor product grows exponentially, right? So this is like a linear growth. And this is an exponential growth. Right? I'll kind of show you this example next time because it's kind of like a nice one to have in mind to illustrate some of the ideas of quantum mechanics. So the idea in quantum mechanics, if you have heard like a qubit, right? A qubit is like a vector in a vector space of dimension 2, right? Because a bit is something that's kind of true or false, right? Or 1 or 0. So the quantum mechanics version of that is like a vector that is in a vector space of which is 2-dimensional. So one basis like is kind of like interpreted as like 0, and the other basis is interpreted as 1. But what happens in quantum mechanics, and that's like what I'll start mentioning next time, is that in quantum mechanics, say you have one electron and another electron, the system that describes both electrons at the same time involves a tensor product construction. Whereas if you had in classical mechanics, one particle and another particle, the system that describes that is kind of like more related to the direct sum or like the Cartesian product, like in terms of sets. So in classical mechanics, things grow linearly, whereas in quantum mechanics, things grow exponentially because quantum mechanics requires like the tensor product. And that's why people, again, if you have heard anything about quantum computations, they say that certain algorithms will become exponentially faster to solve using quantum computation because the quantum bits kind of can store exponentially more information in a sense that the classical mechanics. Okay, so for example, if you had 10 classical bits, like in a sense, like if you think of this state as being 2, like then you get like 20 possible states, but here, like it is kind of like 2 to the 10 or something like that. So it just grows very quickly. But again, I'll refresh some of this next time, but I'll kind of explain to you a little bit of that because it probably is like a more concrete way to think about some of like the quantum mechanical stuff. And yeah, we'll see some more like, it's better to like just see it, I think in this 2x2 case, because otherwise like we don't have that many classes left, so we would just spend too much time in technicality. So here you can see like something like more direct. Okay, so let's just finish here, and so next time I'll start talking about this. That sounds good.